Hello, Mr. Hasty here. Today we're going to be starting chapter 11, which talks about energy. We're going to start with a brief discussion of the different forms that energy can take, as well as a discussion of the work energy theorem, which we covered last chapter. So, forms of energy. We've already talked about one form that energy can take, and that's kinetic energy. Kinetic energy is the energy of motion. We're going to talk about that in great detail a little bit later. There's also potential energy, and more specifically, potential energy due to gravity. So potential energy is energy that is stored but not released. So common examples of potential energy include gravitational potential energy, the energy stored resisting gravity, or chemical energy can be potential because it can be stored in the form of calories until you burn it. Other forms of energy include thermal energy, which is the energy of heat, radiant energy, which is the energy of light, and generally electromagnetic radiation. We're also going to talk about elastic energy. We're going to talk about what's called rest or mass energy, which is has to do with Einstein's theory of relativity. In addition to those, there's also electrical energy, nuclear energy, all these different types of energy that we can discuss. But this section is primarily going to be focused on potential energy and kinetic energy. So the work energy theorem from last chapter basically says that work is equal to the change in energy. So if you can calculate the change in energy of a system, you can calculate the work done on that system. And so what ends up happening a lot is, even though we're using formulas for energy, they'll ask for work. And we just simply need to understand that work would be the change in that energy. All right. Let's review what we know about kinetic energy. So kinetic energy is the energy of motion We're going to use this kind of the basis for our discussion here. So the formula we had for kinetic energy, we had translational kinetic energy, which is subscripted trans here. So 1/2 mv squared. So the units there are, if we think about it, 1/2 is a perfect number, so we're just using that 1/2. But the mass is measured in kilograms, and velocity is measured in meters per second typically, and we're squaring that. So we get a kilogram meter squared per second squared, which we call a joule. Now you might remember work was also measured in joules. Work was calculated as a Newton times a meter. And if we do the math here, Newton is a kilogram meter per second squared. We're multiplying that by meters, and we get the same thing, kilogram meter squared per second squared. Now, rotational kinetic energy is the energy of motion of rotation. I'll call that energy of rotational motion. And the formula there, you wrote, is equal to 1/2 I, which is the moment of inertia, which we know that there are different formulas for different shapes of moments of inertia, times omega squared, omega being the angular velocity. So how could these possibly have the same units? Well, it kind of works out nicely. So again, the 1/2 out in front, there are different formulas for moment of inertia, but one of the most common ones is mass times radius squared. and mass times radius squared. And if we think of angular velocity, what angular velocity is radians per second. Remember, radians are unitless. So let's think about what all this would be measured in. We're going to have a constant with the 1/2. We're not considering that in terms of units. But if we're doing our moment of inertia, we'd be taking a kilogram times a radius. Let's say we measured in meters because we like to measure distance in meters. We're squaring that, the radius squared, times radians per second. We're squaring that. So remember, radians are essentially unitless. So the fact that we have radians squared here doesn't really affect our final answer. We end up getting kilogram meters squared per second squared, which is the exact same unit. It's still measured in joules. All right. The last type of energy we're going to talk about today is potential energy. Potential energy is energy stored due to the interaction of objects. So, examples of this include, as we talked about before, gravitational potential energy. Gravitational potential energy is energy stored due to gravitational pull. Now, what that means is if we have an object that is sitting on something that is preventing it from falling downward, it has gravitational potential energy, because that can be translated into kinetic energy as it falls. So if you suspend something, whether it's held up on a ledge or dangled from a string, that has gravitational potential energy. The formula for gravitational potential energy, GPE, is the mass times the gravitational constant in the situation times the height off the ground, mgh. Now, whenever we're dealing with gravitational potential energy, we have to talk about reference level. And reference level is similar to when we talked about establishing a coordinate axis and a frame of reference for the problem. So a reference level is an established zero height. So most often we call the zero height the ground. However, we could alter this problem by making a hole here, and all of a sudden we have a different height measurement for our situation, a different reference level for our situation. All right. Let's do a few examples here. So example 1, which has more kinetic energy? A 15 kilogram ball moving at 20 meters per second, or a 20 kilogram ball moving at 15 meters per second. And if they start from rest, which ball has more work done on it? So the first thing we're going to establish is we're going to establish the kinetic energy of these objects in motion. Translational kinetic energy formula is 1/2 mv squared. So we're going to have to do this calculation twice, once for the 15 kilogram ball and once for the 20 kilogram ball. So in the first scenario, we have 1/2 times 15 times 20 squared. In the second case, we have 1/2 times 20 times 15 squared. In this first scenario, we're going to get 3,000 joules. In the second scenario, we're going to get 2,250 joules. So, which one has more kinetic energy? the 15 kilogram ball moving at 20 meters per second, because velocity matters more than mass because we square it. So the 15.0 kilogram ball has more kinetic energy. Now, if they start from rest, which ball had more work done on it? Well, the first thing that is important is to understand at rest, both of these objects, because they have a velocity of 0, have a kinetic energy equal to 0. If we look at our formula 1/2 mv squared, if the velocity is 0, that means the kinetic energy is 0. So, which one had more work done on it? Well, work is simply our change in energy. So our 15 kilogram ball went from 0 kinetic energy to 3,000, and our 20 kilogram ball went from 0 kinetic energy, 0 joules, to 2,250. So the one that had the more kinetic energy, we can say thus it had more work done on it. All right, example 2. A 4.5 kilogram hoop starts at rest and begins rotating at a rate of 22 RPMs. Determine the amount of work done on the hoop to create this rotation. So it's asking for work, but remember, work is equal to the change in energy. So this started at rest, so really what we're looking for is we're looking for the final energy, because anytime you have a change in something, it's always the difference between the final amount and the initial amount. We know the initial amount was 0 because it was at rest, so we're looking for the energy at the final amount. So this is rotating, so this is going to be kinetic energy of rotation, which is equal to 1/2 times the moment of inertia times angular velocity squared. So what of this information do we have? And I'm realizing that we needed to know the radius of the hoop. So we'll say that the radius of the hoop is, let's say, 25 centimeters. So in this situation, we don't directly know the moment of inertia, but we can look up the formula for the moment of inertia of a hoop, and that is mr squared times omega squared. So we know the radius. We have to convert it from centimeters to meters, so this would be 0.25 meters. We know the mass. The angular velocity, we usually want that in radians per second, so we're going to have to do our conversion from rotations per minute to radians per second. So, remember that one rotation is 2 pi. If it's 22 rotations per minute, we're converting that. One rotation is 2 pi radians. And 1 minute is 60 seconds. Do that conversion and we will get, to keep it clean, we'll get 11 pi over 30. So putting this into our formula, we get 1/2 times 4.5 times 0.25 squared times 11 pi over 30 squared. We work all that out and we will get 0.19 joules. Now that feels fairly small, but there's a couple things to know. 22 rotations per minute is not even one rotation a second, so it's not moving that fast. Also, with the selection of a radius of 25 centimeters, which I forgot to include in the original problem, it's not a very large wheel. And thus, with those two things combined, means we don't require a whole lot of energy, a whole lot of work to get that amount of motion. All right, let's look at two more problems. All right, example 3. An 8.25 kilogram object is initially held at a height of 45.0 meters above the reference level. Let's draw a quick picture. So it's initially held at a height of 45 above our reference level. We'll call the ground or reference level 0. After 2 seconds, how high is the object and how much work has gravity done on the object? So we have to figure out, if we're looking for work that is equivalent to our change in energy, so we need to figure out the amount of gravitational potential energy at the beginning, and then the amount of gravitational potential energy after 2 seconds. So if we remember, the formula for gravitational potential energy is mgh. And so our initial energy is easy enough to calculate. That's going to be the mass, which is 8.25 kilograms. The gravitational constant, 9.8. And the height, which is going to be 45.0. And we will get, to the 2 sig figs, we'll get 3,600 joules. Now, to find the final, we're missing the height. We know the mass doesn't change. We know gravity doesn't change. The height changes. So we're actually going to need to bring back an old formula from a while ago, and that is our vertical motion equation. In this case, because there's no initial velocity, because it's being dropped, our position at a given time can be modeled as negative 1/2 gt squared plus y naught being the starting height. So negative 1/2 times 9.8, the time squared, so that's 2.00 squared, plus the initial height would be 45.0. Do that calculation and we get 25.4 meters. So our final energy in this situation, 8.25 times 9.8 times 25.4, and that was exact. That was a non-rounded value out of my calculator. So we will get, now appropriately rounded, this would be 2,100 joules. Now the problem with this is that we can't use these rounded values for calculating our amount of work done. We have to subtract the original values. So you could either replug it in or go back and find the original values. But when we do the difference between the two original values, not these two, we get our work is going to be 1,600 joules. Now, I know that that is the same as what you would have gotten if we would have subtracted those, but slight rounding errors in this situation could have been problematic. So you definitely need to have gone back and used the original numbers, not the rounded numbers for those. All right, last one. This one's a bit of a tricky one. A 4.5 kilogram hoop starts at rest and rolls at a speed of 18.0 meters per second. Determine the amount of translational and kinetic rotational motion. So the translational is not hard because we have all the information for a translational. Kinetic energy translational is 1/2 mv squared, and in this case that'd be 1/2 times 4.5 times 18.0 squared. And we would get 729. Now, rounded appropriately, it should be 730 joules. The problem is we don't have near enough information to do our kinetic energy rotationally the same way. But luckily for us, there's going to be some cancellations and some nifty stuff that happens in the formula. So our kinetic energy rotational formula is going to be 1/2 I omega squared. So what we need is we need to think of I in terms of our mass. Our moment of inertia is always related to our mass. So the moment of inertia formula for a hoop is mr squared. So we could solve this in terms of mass, but it's important to just note that it's mr squared. I'm going to put that in there. 1/2 times mr squared. Now omega, we don't have omega, but there is a relationship between angular velocity and rotational velocity. So that relationship is that linear velocity is the radius times angular velocity. We can rewrite this that the angular velocity is equal to linear velocity divided by r. So instead of having omega squared, we're going to have v over r quantity squared. And when we square everything there, our r's will cancel. We can essentially just use the information we have. And turns out the rotational energy is the same as the translational energy. So we get 730 joules for that as well. Now, before you make a conclusion that they will always be the same, that is not the case. If we have one of our different formulas for the impulse, we could end up with a fraction of that number. So for instance, impulse of a solid disk is 1/2 mr squared. If we would have put an additional 1/2 right here, we would have ended up with essentially half the final answer. If it was a different shape, it would be a different fraction there. You can look through the different formulas and kind of see how that would modify. But for a hoop, the translational kinetic energy is the same as the rotational kinetic energy. All right. Tomorrow we'll be talking about other types of energy and how they relate to this information. I'll see you guys then.